Welcome to this explainer. Today, we're tackling something we literally see in the field day in and day out, diagnosing AURUS brand inverter equipment. I know exactly the frustration you feel when you're standing right in front of the unit and the display starts flashing those dreaded E3, E7, or E8 codes. It's so easy to just want to throw in the towel, but hey, we're here to figure this out together. Today, we're going to transform that frustration into a clear, direct, and completely infallible action protocol.
Alright, so what do E7, E8, and E3 actually mean? We really need to shift our mindset right out of the gate here. Instead of seeing this as some catastrophic, indecipherable equipment failure, let's look at them for what they truly are: symptoms. They are crystal clear clues. If we stop seeing a disaster and start seeing a signal that's actively guiding us, and we follow a solid step-by-step method, well, we'll get straight to the solution without wasting hours on the clock or losing our minds.
Here's our game plan for today. First, outdoor unit codes. Second, step 1, physical inspection. Third, step 2, electrical check. And fourth, the final verdict.
Okay, let's dive into this. Part 1, outdoor unit codes, isolating the problem.
You know, unlike indoor unit faults, which can honestly be a real puzzle, these specific codes give us a massive advantage. They instantly isolate the problem right to the outdoor condensing unit, so no more shooting in the dark, checking the entire system end to end. So what exactly triggers these alerts? Well, codes E7, E8, and E3 point squarely at three vital components: the thermistors. We're talking about strategically located sensors that basically take the pulse of the equipment. Their whole job is to send real-time telemetry data straight to the main board. Think of them as the eyes and ears of the machine's brain.
So what actually has to happen for that alarm to go off? The error appears on the display the exact moment the main board stops getting its normal data. This means communication is either completely dead or it's gone totally crazy. The board captures an extreme reading, which really only means one of two things. Either you've got a short circuit or you have a textbook open circuit. There's literally no middle ground for these codes to trigger like that. Moving right along. Step 1, physical inspection, the superficial investigation phase.
We've all been there, right? You see the code flashing and your gut practically screams, "Fried board! We're gonna need expensive parts." But hit the brakes. We've got to resist that panicked urge. Before we do anything crazy, we have to do something super simple but absolutely vital. First, locate the three sensors on the outdoor unit. Second, carefully trace their cables, visually checking their integrity all the way back to the board. And third, disconnect them and reconnect them firmly. We have to ensure that physical anchor to the board is totally solid.
Now, what's really interesting about this slide is why we do this. Think about it. Environmental factors are almost always the real culprits. A little vibration from the equipment running every day, or that typical sulfation caused by the weather, and bam, you've got a false contact. That's honestly enough for the equipment to throw an error and completely lock down, even if the physical sensor itself is perfectly fine. Skipping this and going straight to replacing parts is just throwing money down the drain.
All right, part 3. Step 2, electrical check. Time for the deep analysis. Let's say you've cleaned everything, reconnected the cables, it's all tightly anchored, you restart the equipment, and damn it, the code is still there. Okay, no problem. We just moved down our diagnostic funnel. Visual checks aren't enough anymore, so it's time for a deep, authoritative analysis. Pull out the star tool of the trade, your multimeter. And listen, this is absolutely crucial. It has to be specifically set to the ohms scale. We can't just measure resistance by eye. That's totally useless. Setting the multimeter to ohms is strictly mandatory to measure that component's resistance with millimeter precision. We need to see what's actually going on inside the sensor's electronic guts.
For this step, it is vital to have the AURUS manufacturer's technical table on hand. Why? Because we have to cross-reference the actual ambient temperature at that precise moment, right where we're working, with the exact target resistance shown on the manufacturer's table. This step, my friends, is pure math. It's totally infallible and just eliminates all guesswork. While you're taking these precise live readings, you have to be super alert. We are basically hunting for 3 specific red flag scenarios with our multimeter. 1, readings that fall completely outside the table's ranges. 2, a reading of infinite resistance. Or 3, values plummeting absolutely to 0. And this brilliantly illustrates our first extreme case. If you see a 0 on your screen, the data is speaking to us loud and clear. A value dropping straight to 0 mathematically proves, without a shadow of a doubt, that you've got a direct short circuit inside that piece. The sensor has failed.
On the flip side, if instead of 0, your reading jumps to infinite resistance, well, that confirms a textbook open circuit. The internal connection of the sensor is just completely broken. Electricity literally cannot flow anymore.
Which brings us to part 4, the final verdict, resolution and diagnosis. With all this electrical data clearly laid out on the table, the doubts are over. It's time to make a confident, professional call and get this equipment fixed once and for all. Looking at the numbers, using clear if-then logic, we're inevitably looking at 2 very different scenarios. On the left, we've got Scenario A, a damaged sensor, and on the right, Scenario B, which is a bit heavier, a damaged board. Let's break down how to make that ultimate call.
So, walking through Scenario A, which is definitely the most common, if the resistance measurement is straight up out of the table's range, it's clear as day that thermistor is dead. The solution here is direct. Just replace it with a new sensor of identical capacity, reconnect it, and boom, problem solved. But pay really close attention to Scenario B. It's less common, but super critical. What if you measure it, and the resistance is perfectly normal for that ambient temperature? Well, paradoxically, that proves the sensor is actually fine. And if the sensor is sending the correct signal, but the machine is still throwing an error, the fault is isolated in the brain receiving that signal. Meaning, your outdoor electronic mainboard is faulty, and you've got to replace the entire board. Before we wrap up, I really want you to take away this core philosophy. Dominating this step-by-step investigation is exactly what builds a solid reputation as a fast, resolutive, and professional technician. Relying on pure data rather than blind guessing, that completely transforms your daily efficiency. It's a real game changer. And so, we end this explainer leaving you with something to think about. It's wild to see how a smart, data-driven diagnosis just changes the rules of the game. So how much time, money, and sheer frustration will you truly save on your next repair by applying this strict mathematical method? Ditch the old guessing habits, follow the data, and completely dominate your next diagnosis. Thanks for joining us, and we'll see you on the next explainer.